When you think about number theory is a fascinating concept in mathematics in which we try to learn more about the numbers. But when we think about numbers, there are many types of numbers like positive numbers, negative numbers, zero, rational numbers, irrational numbers, maybe complex numbers. And you can learn about all of them, their properties, and how they behave with each other. And the most interesting aspect of the number theory study is often prime numbers because they are very peculiar, because they have only the divisor themselves and one, and they give a lot of property to understand and find the equation and the properties rather than the natural numbers or the whole, all of the numbers. So if we have select numbers which behave in a similar way, often the prime numbers give us a very distinct view of the number theory. So we study all the numbers and how they behave with each other. For example, we write a number, let's say A is congruent to another number B, mod another number C. So what does it even mean? It means that we have to first define what does this all of this mean. It means that the modulus of a number means that number divides the difference of the both the numbers. That means n divides a minus b. That is we have defined a certain way of seeing numbers, and then we go about finding the properties and equation and how they fit into our society and problems and how other things might connect into it, and that might help us solve different problems related to numbers because we have defined a new concept, a congruent to b modulus of c. So how do you go about that? It can be anything like 5 is congruent to 5 modulus of 10, because 5 congruent to 5 means 5 minus 5, 0, and every number divides 0. So you can write 5 congruent to 5 modulus of 10, 20, anything. Or you can write 11 congruent to 1 modulo of 5, because 11 minus 1 is 10 and 10 is divisible by 5. So that's one way to look at it. So is there how many things, how many concepts are there in number theory? And I would say a lot. And the concepts keep on increasing and day by day, and it gives a peculiar way of thinking how the number systems work and how they give us a property and how we can solve much bigger problems. Like when you think about a problem like a raised to n plus b raised to n is equal to c raised to n, that's a number theory problem. Like it was given by Fermat's last theorem, and it was scribbled in his notebook, and it was a conjecture at that time. But now we know it's a proof that it was can a raised to n plus b raised to n is equal to c raised to n doesn't have a solution when n is bigger than 2. So we know we have found out that when the n is 1, so we get simply a plus b is equal to c, and we can find a solution. 5 plus 3 is equal to 8. We have a solution. But in natural numbers, I must say, but when we write 2, we have the solution because it becomes a Pythagoras theorem. A square plus b square is equal to c square. One side plus another side square is equal to hypotenuse square. And we have a solution. When it becomes cube, 4, I don't know if it has a solution or not. And Fermat did not give us a solution in his scribbling on the notebook. And we had to search for it. And for many, many years, we did not have a solution until another mathematician gave a solution of almost more than 120 pages and was long, and he got a very good, nice prize for that, and he was applauded, lauded. But the proof involved proving something entirely different, using that thing and trying to find a solution for a seemingly simple equation in number theory. And you might ask, what is the point of all this? The thing is, in mathematics, also in science, you don't do something because you have a point or you don't have a point, because the applications connections might come up everywhere. One thing might be needed to solve something entirely totally different, and that might be helping something another else. So everything mathematically a problem is a problem worth solving, and the more basic the problem is, sometimes the more difficult it becomes to prove it, like the Collin's conjecture or the Fermat's theorem. So we might get a proof like in the Fermat's theorem, but we are always looking for an elementary proof, something called a simple proof, which we can understand in a better way with a much less concepts. So see how our knowledge and our thinking has gone. So that's an introduction to number theory. I would say lots more. Depth is like a valley, the breadth is like thousands of valleys. See you next time.